In this video, we are going to discuss the ways in which we can express solution concentration quantitatively. There are several ways that we can express concentration. We should be familiar with the first from General Chemistry 1, molarity. Molarity is designated by a capital M and is defined as the moles of solute per liters of the solution. Remember that the liters of the solution is going to encompass both the solute and the solvent. Molality is another way in which we can quantify concentration. It is designated by a lowercase m, and it is defined as the moles of solute per kilograms of solvent. Mole fraction, designated by x, is just a ratio of the moles of solute to the total moles of solution. Remember that the moles of solution is going to be the sum of the moles of solute and the moles of solvent. And mole percent is actually taking the equation from mole fraction and multiplying by a factor of 100. Essentially, this converts the fraction or decimal into a percent. We also have the units of parts by mass or parts by volume, which are both very similar to each other. Both of them can be expressed in terms of percent, parts per million, or parts per billion. Parts by mass is the ratio of the mass of solute over the total mass of solution, i.e. solute plus solvent, times some multiplication factor, which depends on the units that you would like to express it in. We can see that parts by volume is very similar. However, you use the volume of the solvent compared to the volume of the solution. So the multiplication factor is dependent on the unit in which you would like to express parts by mass or parts by volume in. If we would like to express it in terms of percent, the multiplication factor would be 100, similar to what we did for the mole percent. If the value should be expressed in parts per million, the multiplication factor will be 1 million or 10 to the 6th. If the value should be expressed in parts per billion, the multiplication factor will be 10 to the 9th, which is 1 billion. Now, in order to remember these quantitative measurements of concentration, I would definitely suggest making some flashcards and just practicing a lot of problems in order to help you remember these mathematical definitions. Ultimately, you're not going to be able to solve the problems unless you know what these mathematical definitions are. As I said, the best way to help you remember these is to practice. So let's try a practice problem where we solve for each concentration unit. We are told that a solution is prepared by dissolving 50.4 grams of sucrose into 0.332 kilograms of water. The final volume of the solution is 355 milliliters. We're asked to calculate the concentration of the solution in each of the following units. When we're reading a word problem, it is best to pick out the important information. We're told that there are 50.4 grams of sucrose in 0.332 kilograms of water. We can define sucrose as our solute and water as the solvent. We are also given the final volume of the solution, which is 355 milliliters. Now first, we're asked to find molarity. We need to find the two different components that make up molarity, the moles of solute and the liters of solution. So what information do we have that corresponds to solving for molarity? Well, we were given the mass of the solute, which is 50.4 grams of sucrose, and the final volume of the solution, 355 milliliters. Now we just need to convert the grams of solute to the moles and milliliters of solution to liters of solution. In order to convert the grams of sucrose to moles, we need to first calculate the molar mass. Since we know the chemical formula of sucrose to be C12H22O11, we can use the molar masses on the periodic table to determine the molar mass is 342.29 grams per mole. Remember, molar mass is the only conversion factor that we can use to convert grams to moles or moles to grams. Since we are converting from grams to moles, we need to divide by the molar mass in order for the units of grams to cancel. We determine that there are 0.147 moles of sucrose. In order to convert 355 milliliters to liters, we must recall that there are 1,000 milliliters in 1 liter. Therefore, there is 0.355 liters of solution. Ultimately, we can now plug in the numerator and the denominator to calculate the molarity. So we take the ratio of 0.147 moles of sucrose to 0.355 liters of solution and determine that the molarity is 0.415 molar. We report this value to 3 sig figs because we are taking the least number of sig figs from these two values based on the rules of multiplication and division. And since each of these values only has 3 sig figs, we have 3 sig figs in our final answer. Now to calculate molality, we need to figure out the moles of solute, which we actually just calculated in part A to be 0.147 moles of sucrose. So when you're doing these types of problems, make sure that you write down your work and keep it organized so that you don't have to go back and recalculate certain values. And in the initial problem, we're actually given the kilograms of solvent, which is 0.332 kilograms of water. We now have the two components that make up molality, so we can take the ratio of these two values and determine the molality to be 0.443. Now, in order to calculate percent by mass, we need to know the mass of the solute and the mass of the solution. But remember, the mass of the solution is going to be the mass of solute plus the mass of solvent. In the initial problem, we are given that we have 50.4 grams of sucrose, the solute, and 0.332 kilograms of water, the solvent. In order to convert the mass of water to grams, we need to multiply by 100 since there are 1,000 grams in every 1 kilogram. Therefore, we have determined that we have 332 grams of water. So, to solve for the percent by mass, we will plug in the mass of the solute, 50.4 grams of sucrose, over the mass of the solution, which is equivalent to the mass of the solute, 50.4 grams of sucrose, plus the mass of the solvent, 332 grams of water. Times this fraction by 100 in order to make the value a percent. Ultimately, we determine that the percent by mass of sucrose is 13.2%. In order to calculate the mole fraction, we need to know the moles of solute and the moles of solution, solute plus solvent. We previously calculated that there is 0.147 moles of sucrose in solution, but we do not know the number of solvent moles present. Since we just calculated that there are 332 grams of water in solution, we can divide by the molar mass of water, which is 18.02, in order to convert grams to moles. We thereby calculate that 18.4 moles of water are present. Plugging in these values, we take the moles of the solute, 0.147 moles of sucrose, over the moles of solute, 0.147 moles of sucrose, plus the moles of solvent, 18.4 moles of water. Ultimately, we calculate the mole fraction of the solute, sucrose, to be 0.00792. This is a unitless value because the moles on the numerator and the denominator cancel out. It is important to note that if you ever calculate a mole fraction that is greater than 1, you need to redo this calculation. You can never have a mole fraction that is greater than 1. In fact, if you add up all the mole fractions of the components that are in solution, they should combine to equal the whole solution, which should be equivalent to 1. The last thing we need to solve for is the mole percent of the solution. Since we have calculated the mole fraction, the calculation is quite easy. We will simply plug in the mole fraction and multiply it by 100 to convert it to a percent. If we multiply the mole fraction we previously calculated, 0.00792, times the factor of 100, we get the mole percent of sucrose in the solution to be 0.792%. So overall in this video, we have learned the definitions and practiced calculating the various ways in which solution concentrations are expressed quantitatively.